Good morning to all of you. Today I am recording the video lesson for day 8. So we have been discussing about the simple stresses and strains. Today we will study about the thermal stresses. So we will go into deep about the thermal stresses and we will study about the thermal stresses in simple bars and also in composite bars. For that I have prepared the PPTs for today's lesson, and now we'll go by PPT. So today we'll discuss about the thermal stresses in uniform bars, uniform sections, and also in composite sections. At the end of this lecture, we'll be able to find out the thermal stresses in the bars of the uniform cross section, and also we will able to calculate the thermal stresses in the composite bars, and also we'll learn some of the definitions related to the thermal stresses. So actually what is the thermal stress? So it is important to note that the term indicating that it is a thermal stress means what? The stresses developed in the material due to the temperature. The stresses induced in the materials due to the rise or fall of temperature, and when the corresponding elongation or contraction is avoided, then the stresses developed in the bars are termed as the thermal stresses. If you see, it is a body, it is a metal bar, or for example it is a mild steel bar. So this bar is subjected to increase in temperature. So whenever any material is subjected to increase in temperature, naturally it elongates, the length will increase. So the amount of increase in length will depend on some factors. So for that we got, so it's all depending on its material property, because it also depends on the coefficient of linear expansion, and also it also depends on the amount of temperature rise, that is the difference of final and initial temperatures dt, and also it's all depending on, it is proportional to the original length. So if the original length is more, automatically the increase in length also will be more. Like this, the increase in length or the expansion of the material will depend on some factors. But however, whenever a material is subjected to heating, or we can say the increase in temperature, the length of the bar increases, it expands, and we can able to find out that expansion by using some formula. And on the other hand, whenever a material subjected to decrease in temperature, that means if the difference in temperature between the final state and initial state is negative, that is it decreases, then the material contracts. And so this way, this is a fundamental thing. Whenever a material is subjected to heating, it expands, and whenever a material subjected to cooling or decrease in temperature, the material contracts. And however, the amount of expansion and the amount of contraction will depend on some factors, and that can be discussed later on. And here in the present case, so it is a metal bar subjected to increase in temperature. So when it is subjected to increase in temperature, naturally the delta L, so it expands or the length increases. So the increase in length is equal to, say here we can say L is equal to the length of the bar, delta L is the deformation or the increase in length, or we can say it is the expansion of the bar, and delta T is the change in temperature, and alpha is called as the coefficient of thermal expansion. So it is also called as the coefficient of linear expansion, and it's depending on the type of material, that is the nature of the material, and its value will be constant for a specific material, and its value is different for the different materials, and its unit is per degree centigrade. Now, if you see the when this metal bar is subjected to increase in temperature of delta T, the length will expand. So initial length L is, and we got a final length of L plus delta L, or the delta L is the increase in length, or we can say it is a expansion, and that delta L can be found by using the relation delta, the change in length, or in this case it is increase in length due to the rise in temperature. Delta L is equal to L into alpha into delta T, where L is called as the original length of the bar, alpha is called as the coefficient of linear expansion, and delta T is called as the change in temperature. So here what is happening is, whenever the body is subjected to rise in temperature, the final temperature will be more and initial temperature is less. The difference will be positive. So here delta is positive. In the other case, when the body is subjected to cooling, or it is subjected to decrease in temperature, there the final temperature is lower than that of the initial temperature, and the difference of the final temperature and initial temperature will be negative. So therefore, there the delta L will be negative, and it causes the contraction of the material. And if the delta L is positive, then we can say it will expand. If the delta L is negative, then the material will contracts, the length will decreases. That you must note. And in the present case, we are considering only the increase in the temperature, so it expands. Now, if you say that the same bar is shown in the three figures, that is figure 2, A, B, and C. So, the figure A, that is the initial bar having a length L at normal condition, and the figure B is the view of the bar at the elevated temperature, at the increased final temperature. So when the bar is increased to some final temperature T2, from T1 to T2, then due to the increase in temperature, the length of the bar increases, or that it causes an elongation. So that amount of elongation or the expansion is equal to L into alpha into T. Now the final length will become that L plus delta L, that is nothing but the L plus L alpha T. That is the final length of the bar due to the increase in temperature. And when this expansion is allowed, so there is no stress developed in the bar. We must note that when the bar is allowed freely for expansion and there is no obstruction for the elongation, so no stress will develop. No stress will develop due to the rise in temperature. But when this free expansion of the bar is obstructed, when this free expansion of the bar is restricted, then it will not expand. So actually when it is freely allowed, it will just expand and then no stress will be there. When that free expansion or the contraction is avoided or restricted, then that amount of, so then it would have been freely allowed to expand or contract, then some amount of delta LV will be produced. When it is not allowed to, when it is not allowed freely to expand or contract, so what is happening is the amount of delta L will be there. So when it is freely allowed, it will produce some delta L. When it is not allowed freely, whatever the amount of expansion or contraction that would have been produced in the bar will be restricted, and correspondingly some amount of strain will be produced. The amount of strain will be equal to nothing but what is the strain value? Change in length by original length. So delta L by L, L alpha T by L. So that becomes the alpha into T. So that strain will cause the stress in the material, and these stresses are called as the temperature stresses or the thermal stresses in the bars. And this generally the temperature stress induced in the bar is directly proportional to the change in temperature and also directly proportional to the length and directly proportional to the change, that is the length and temperature. So therefore the stress will be equal to, and it is also bears a constant ratio with the coefficient of linear expansion. So like this, so we must know that here whenever a body is allowed freely to expand or contract due to the change in temperature, no stress will be developed. But whenever that expansion or contraction is avoided, then the bar is subjected to the strain as if it is subjected to some kind of load due to the change in temperature, and that it is subjected to some kind of stress. That stress is called as the thermal stress or the temperature stresses. Now we know that when the expansion is prevented, what is happening? The body is subjected to a compressive force. So here what is happening is whenever the pre-expansion is avoided by a support, then the body is subjected to, as if it is subjected to compressive force, and a compressive stress will develop. And whenever a body is subjected to decrease in temperature and that pre-contraction is avoided, then the body is subjected to a tensile force. In the present case, the body is subjected to increase in temperature, and that free expansion is avoided. Here, this body is subjected to the compressive stress and also compressive strain. And we know that the compressive strain value is equal to delta L by L. So that is nothing but the L into alpha into dt by L. So this is equal to alpha into dt. So that is the strain. Now stress is equal to modulus of velocity into strain. So the compressive stress sigma is equal to E into strain. So here we got the strain value is equal to alpha into delta t. So the stress is equal to E into alpha into delta t. So the thermal stress induced in the bar is equal to E into alpha into t. And here, for example, in this case, the body is the expansion of the bar expansion of the bar is allowed to some extent. It is not fully prevented. The free expansion is not fully prevented, and whereas the free expansion is allowed to some extent to the amount of delta, and after that it is prevented. After that the expansion is prevented. Now the last figure shows that the bar is stopped by a support after allowing its expansion up to an amount of delta. Now, actually, if the bar is subjected to increase in temperature, the final length would be L into alpha into delta T. However, we are allowing the free expansion of that bar up to delta amount. So, now the prevention of the change in length. So, to what extent we are preventing is nothing but the L alpha T minus delta. This is the effective compression that we are stopping to expand, and this leads to development of the stress in the bar. So now the strain is equal to, we know that delta L by L. Here the delta L, how much the length is prevented is equal to L alpha T minus delta. So L alpha T minus delta by L. So it becomes E is equal to alpha into T minus delta by L. So the temperature stresses in this case is equal to E into alpha into T minus delta by L. Now we will like to solve some problems on this temperature stresses to have the better understanding of the concepts. Now we must note that whenever a body is subjected to increase in temperature and that pre-expansion is avoided, then it is subjected to compressive force. And whenever a body is subjected to decrease in temperature, that is cooling, and pre-contraction is avoided, then it is subjected to a tensile force, and the tensile stress will be developed in the bar. That we must note. And here the amount of stress induced in the material also will be depending on the coefficient of thermal expansion and the change in temperature. Now we can write down this problem and accordingly we'll solve it. A steel rod 2 meters long is fixed rigidly at the ends and heated through a temperature of 100 degrees centigrade. Find the stress induced in the rod if alpha s is equal to 12 into 10 power minus 6 per degree centigrade and es is equal to 2 into 10 power 5 newtons per square millimeter. What is the expansion prevented? So this is the problem given. So now we can go for the solution. First of all, we should write down the given data from the problem. The first one is length of the rod is given. L is equal to 2 meters. So that is equal to 2000 millimeters because we have to convert all the things into millimeters and square mm wherever it is required. Now they said that it is here what they said so and heated through a temperature of 100 degrees centigrade. That means it has been raised to a temperature of 100 degrees centigrade. That means initially it was having, we are presuming that it is at 0 degrees centigrade or the change in temperature delta T is equal to 100 degrees centigrade. Here the initial temperature is not given, only they said that heated through a temperature or heated to a temperature of 100 degrees centigrade. That means we are assuming that the difference of temperature is equal to 100 degrees centigrade and delta T is equal to 100 degrees centigrade. Now the coefficient of linear expansion is given. So alpha for steel is given as 12 into 10 power minus 6 per degree centigrade. Next, the modulus of velocity or Young's modulus for the steel ES is equal to 2 into 10 power 5 newtons per square millimeter. Now coming to the solution part, here the stress can be found by finding the strain value. First of all, we have to find out the strain. So how the strain can be found? The strain is nothing but the ratio of the delta L by L. So if the here what is happening is in the given problem the both ends are fixed and the expansion is prevented. So therefore, so we'll find out the amount of expansion or amount of increase in length if the bar would have been allowed freely. So if the bar would have been allowed freely, then it would have been produces an elongation delta L is equal to L into alpha into delta T. So that is equal to 2000 into 12 into 10 power minus 6 into 100. So it comes to be 2.4 millimeters. Now the strain, we know that the linear strain is equal to ratio of the change in length by original length. So delta L by L. So that is equal to 2.4 by 2000. That is the original length. So it comes to be 1.2 into 10 power minus 3 because it has not having any units. So that is the value only. Strain is equal to 1.2 into 10 power minus 3. Now we know that the stress induced, the stress we know by the equation stress by strain is equal to Young's modulus, and whereas the stress is equal to strain into Young's modulus. So strain is given as 1.2 into 10 power minus 3, and Young's modulus is given as 2 into 10 power 5. So multiplying the two values, we'll get the stress value is equal to 240, and the unit is, because all we have taken in millimeters and Newton per square millimeters. So therefore the stress induced will get the in Newton per square millimeter. So in the present case, the value of stress, that is the thermal stress, is equal to 240 newtons per square millimeter, and also the elongation already we have found. So the amount of, so what they asked, the what is the expansion prevented. So the expansion prevented is equal to 2.4 millimeters. So these are the answers. Now next we'll go to the other problem. Now, so it is a problem here, the initial temperature, final temperature are provided, and we are supposed to find out the intensity and the kind of stresses, that is nothing but the intensity, and also the nature of stresses developed in the bar. Now for this, firstly we have to write down the problem. New steel railway rails, new steel railway rails, new steel railway rails were laid at a temperature of 12 degrees centigrade with 3 millimeters gap at each end. The rails were 10 meters long. During the summer, the temperature rose to 45 degrees centigrade. Determine the intensity and kind of stress developed. Take alpha S is equal to 12 into 10 power 6 per degree centigrade, and ES is equal to 2 into 10 power 5 newtons per square millimeter. So here what is happening is, the newly constructed railway line has been laid with new steel rails and they are having a gap of 3 millimeters. So a gap is there. So here what is happening is, here they are laid down at 12 degrees centigrade. Now in the summer the temperature goes to 45 degrees centigrade. So there is a increase in temperature. So here what is happening with this, here some, however, some gap is kept between the two rails in order to allow the expansion. If the, here what is happening is, the amount of gap left over is 3 millimeters. If the increase of the rail due to the rise of temperature is only within 3 millimeters, then no stress will be developed. And if at all the expansion of the rail is more than 3 millimeters, then it will go beyond the gap. Whereas it will not, then after allowing an expansion up to 3 millimeters, then the expansion of the rail is stopped. Then it starts increases, it starts inducing the stresses in the bar. So they are the thermal stresses. So that we have to count. Now coming to the solution, first part is we have to find out the, we have to write down the given data from the problem. The first one is the initial temperature is 12 degrees centigrade. Final temperature T2 is equal to 45 degrees centigrade. Here the increase in temperature delta T is equal to T2 minus T1, that is equal to 45 minus 12, that is equal to 33 degrees centigrade. So that is the change in temperature. Now the length of the rail is given as 10 meters, that is equal to 10 into 1000, it becomes 10,000 millimeters. Here yield provided, so there is gap provided between the two rails. So up to that 3 millimeters, it is freely expanded. The free expansion is allowed up to 3 millimeters, and beyond 3, if at all the rail expands beyond 3 millimeters, then only that free expansion is avoided by the other rail present at that point, and that induces stresses, and that we have to find out. So we know that the expansion of the rail or the thermal deformation delta L is equal to L into alpha into delta T. Here L is equal to 10,000, alpha is equal to 12 into 10 power minus 6, and delta T is equal to 33. So by substituting those values, we'll get the thermal deformation delta L is equal to 3.96 millimeters. Now here what is happening is, the delta L is more than the yield given. So up to 3 millimeters they are free to expand. But the expansion of the rail comes to be 3.96. So what is happening is, only the remaining part, that is how much will be subject, will cause the, so up to 3 millimeters it will not cause any stress, and because it has been increasing to 3.9, the 0.96 millimeters will cause the, when that 0.96 is allowed by the other rail, the pre-expansion of the this 0.96 is allowed, not allowed by the other side rail present, then this is will cause the stress. And here we know that the strain formula, strain is equal to alpha into delta T minus delta by L. So by substituting the values, so we'll get strain E is equal to 9.6 into 10 power minus 5. That is the value of the strain. And here we know the what is happening. Here the thermal expansion is more than the allowed gap between the rails. Therefore, the free expansion is avoided by the rail present at the other side. So here this rail is subjected to what the compressive force. Here what is happening? The free expansion is avoided. So this rail is subjected to a compressive force, and the amount of compressive stress is equal to strain into Young's modulus. So strain value we know, that is 9.6 into 10 power minus 5, and Young's modulus is given as 2 into 10 power 5. So by substituting those values in the equation, the compressive stress is equal to 19.2 newtons per square millimeters. So here in this problem, the thermal elongation of the bar or the thermal expansion of the bar is more than the gap allowed between the rails. Therefore, the free expansion of the rail is avoided. Therefore, the rail is subjected to some kind of stress, and here in this case it is the heated, it is subjected to heating or subjected to increase in temperature, and that free expansion is avoided. Therefore the compressive stress will develop in the rail. So amount of compressive stress developed is equal to 19.2 newtons per square millimeters. Now in this class we have discussed about the thermal stresses, and also solved some of the problems on the thermal stresses to have the concepts on the thermal stresses. Now, so what is the thermal stress? Now coming to the summary part, what is the thermal stress? The thermal stress is nothing but the stresses induced in the bars when they are subjected to change in temperature are called the thermal stresses. The thermal stresses are nothing but the stresses induced in the bars, and the free expansion or the contraction is avoided. Then that stresses are called as the thermal stresses. And if the bars are, in this case, if the bars are freely allowed to expand or contract, then actually no stress will develop. Whenever the free expansion or contraction is avoided either fully or partially, then the bars are subjected to some kind of strains, as if the bars are subjected to forces, and due to that some amount of stresses are induced in the bars, and that stresses are called as the thermal stresses. And in this case, whenever a body is subjected to some increase in temperature, that is, it is subjected to heating. The heating, what happens? Initially, it is having a low temperature, and finally, it will be having the more temperature, that is high temperature. The change in two temperatures, that is final temperature and initial temperature, will be positive in case of the heating, and the difference of the final temperature and initial temperature is negative in case of cooling. So therefore, in case of heating, the bar is subjected to actually expansion, but that expansion is avoided. So the bar is subjected to a compressive force. Here what is happening is actually the length of the bar would have been increased to some extent, but that increase in length or the elongation is avoided by application of some kind of forces, we can say. So what can to avoid that elongation, or to withstand that elongation, so we have to apply the compressive force. So here what is happening is the ends of the the bars are subjected to a compressive force. Here what is happening? For example, the bar is fixed in two supports, and the bar would like to expand, but the supports are not allowing the bar to expand. Here what is happening? The ends of the bar are subjected to two equal and opposite push type forces, and therefore this push type forces will produce the contraction in the length generally. So that means whenever a bar is subjected to increase in temperature, and that free expansion or free elongation or the deformation due to the rise in temperature, that is called the thermal deformation, is avoided or restricted, then compressive stresses are induced in the body. And similarly, if a body is subjected to decrease in temperature, and that free contraction, whenever a body is subjected to decrease in temperature, the body will contract, but when that free contraction is avoided, then what happens? The the body is subjected, the ends of the body. What is the body is fixed between the two supports? The body will try to contract, but the end supports at which the ends are fixed will not allow the body to freely contract. So in this case, the body will be subjected to two equal and opposite pull type forces. So nothing but the tensile forces, and as a result of which the tensile stress will be developed in the bar. So therefore, whenever a body is subjected to increase in temperature, and the free expansion or contraction is avoided, then the compressive stresses will be developed. And similarly, whenever a body is subjected to decrease in temperature, and the pre-contraction is either completely prevented or restricted, then the body is subjected to the tensile forces, and the thermal stresses will develop the tensile stresses. So in both the cases, the stresses induced in the materials are called as the thermal stresses and are the temperature stresses. So this is about the thermal stresses in the bars of uniform sections. In the next class, we will discuss about the thermal stresses in the composite bars, so that a bar made up of the two or more materials, but when it will act like a single unit, then that bar is called as the composite bar, and the effect of temperature and the thermal stresses in the composite bars will be discussed in the next lesson. So thank you all.